nu with minus nu, the curvature changed sign, so this quantity here, this vector is invariant. Okay, that's the mean curvature vector at a point, and it defines a normal vector field along the surface. But now let's say we have a family of smooth surfaces. Okay, so MT, where T lies in some interval I. So we'll think of T as time. And so this is really just one surface that's moving in time, so it's a time-dependent surface. And then you can think about the velocity of this moving surface as a vector field along the surface. So at each moment in time, one way to think about the velocity is as a normal vector field along the surface at that time. And so this evolving surface is a mean curvature flow if those two things agree. Okay? So at each moment in time, the velocity field should be equal to this geometrically defined vector field, the mean curvature vector field. Okay?
How do you define the direction?
Well, so at each point, you can choose a normal. You take the sum of the principal curvatures with respect to that normal, and you take the product. Okay? So that product is invariant under the choice of normal. So it's a canonically defined vector, normal vector at that point. Okay?
It points in the sense that the thing is curving, right?
So if you have a sphere, it will point the direction in the direction the surface is curving toward into it. Okay? So that's one definition. So another way to think about this is in terms of graphs, right? So if you have an evolving surface, so locally in space-time, an evolving surface is just the graph of a time-dependent function. Okay? So you take some function, say u sub t, this domain with domain some open set in R2, taking values in R. Okay, and so you take the graph, maybe over the xy plane, maybe over one of the other coordinate planes, and so that's a little piece of your evolving surface, right? And the graph of that time-dependent function will be a mean curvature flow if and only if the function satisfies this PDE. Okay, so it's easy calculation. So it says the time derivative of that function should be the square root of 1 plus the gradient squared times the divergence of this, right? Putting aside the details, you can see that this right-hand side is a linear combination of the second derivatives. It's a linear combination of the second derivatives of this function u, where the coefficients depend on the first derivatives. Okay, so this is a quasi-linear equation. It's a parabolic equation. So yet another way to think about the same thing is in terms of parameterized surfaces. Okay, so you can think. So let's say we have now we have a family of embeddings, ft. So here n is some fixed abstract surface, and we take a family, time-dependent family of embeddings, f sub t, embedding this abstract surface into R3. So then we can ask that the time derivative of the embedding is equal to the Laplacian of the embedding. Okay. So with the caveat here that this delta t, okay, the delta t here is referring to the Laplacian that's associated with the induced metric at time t. Okay, so at time t you have an embedding into R3. You look at the induced metric on the that surface sitting in R3. Okay, and then you pull it back and you think of that as a metric on the domain. So you have a time-dependent metric on the domain that has an associated Laplacian. So that's what that thing is there. So if you're a little sloppy, you might just think that this looks like the heat equation. Okay, but that operator actually depends on time in this way. So it's not quite the heat equation, but it looks a lot like it. Okay, but in any case, if you look at the images of these guys, you get a surface moving in time, and that will be a mean curvature flow, and you can reverse this construction. Okay, so that's another way to think about it. Another way to think about it is that mean curvature flow is a gradient flow, or a steepest descent flow. So here, that's just saying, you think about the space of all surfaces in R3 as some sort of infinite dimensional manifold, and then you have the area function on that, and so then you can interpret this as the gradient flow as follows. So if you give yourself a vector field C along the surface, then the first variation formula for area says this. So if you push the surface in the direction of this vector field, then the derivative, or the variation in the area, is given by this first variation formula, right? So you take the variation vector field, inner product the mean curvature vector, integrated over the surface. Thought another way, that's just saying we take the L2 inner product of the variation C with minus the mean curvature, okay? Using the natural kind of Hilbert space structure on the vector fields along the surface. So, or in other words, that's saying that the mean curvature is minus the gradient of the area. This is a formal calculation, right? All right, so some of what I'm saying applies to hypersurfaces in any dimension, and
You're reducing the area.
right. It's the steepest descent for reducing area.
Here it has to go this way.
Right. And some of it applies in higher codimension, but I mean, once we get beyond the beginning part of the theory, it's going to be hypersurfaces only, and probably only surfaces in R3. Okay, so a little bit about the history. So mean curvature flow actually, it shows up as a natural mathematical model of a variety of physical situations. Okay, if you have a surface where the energy is proportional to area and you can neglect inertial effects, then the equation is going to be mean curvature flow. The surface might be a film, like a soap film. It might be a membrane, or it might be just the interface between two different substances. And in fact, this first showed up in the physics literature in the 1950s in the metallurgy literature in connection with annealing of grains of metal. Okay, but I should mention that so you do actually get mean curvature flow as a natural model in many contexts, but there are far more situations where the equation has mean curvature plus some other term, which at least when things get interesting can be viewed as a perturbation. Okay, so it's natural to study this as kind of a first case. If you understand mean curvature flow, then you have a better chance of understanding these more complicated equations. So now it also can be used in various problems in geometry, well, topology also, and in physics, I mean, at least say in general relativity. From another point of view, if you're a PDE person, right, mean curvature flow is a fundamental PDE, right? And we already saw that it almost looks like the heat equation, right? It's a natural version, analog of the heat equation. If you have an evolving surface, and if you'd like to think about minimal surfaces, well, then this is the parabolic analog of the minimal surface equation. All right. Now, mathematicians have been looking at this for a long time, since the late 70s, using different tools, using geometric measure theory, differential geometry, and also more conventional PDE techniques. And it's been a fascinating topic from different points of view. Okay, so now I want to look at some special solutions. So the simplest one would be just a static plane. The plane has zero curvature, so if it just sits there, that's a solution. So a variation on that would be to just look at a minimal surface. So a surface is minimal by definition if the mean curvature equals 0, right? So that's also a solution. In particular, I mean, there's a zoo of examples of minimal surfaces. Those are solutions to mean curvature flow. But note that by this remark, you can think of mean curvature flow as kind of, at least in terms of complexity, as kind of containing the complexity of the theory of minimal surfaces. It's not quite accurate, but I mean, it's, it is, a lot of the elliptic theory is kind of subsumed there. Okay, so the first interesting solution would be the case where you take a round two sphere. So take the unit sphere, and then you let that evolve under the mean curvature flow. So you can check that, right? So the mean curvature points inward, right? The principal curvature of a sphere of radius r is 1 over r. So as it shrinks, the curvature gets bigger and shrinks faster and faster. You can solve this explicitly, right? So the radius at time t will be 1 minus 4t. So that radius goes to 0 as t approaches 1/4, and the curvature blows up. Okay. Now, if you start with the shrinking, start with a round cylinder, so the unit circle of cross r, then that will shrink, and it will shrink down to a line as time approaches 1/2. So let's look at the first properties. So you have short time existence theorem. So this goes back to, I think, the 1930s. Right? If you have a compact smooth surface, well, then you can solve this equation uniquely for short time. Okay? So there's a unique mean curvature flow. It's defined on some time interval 0, epsilon. Right? So here M0 is your prescribed surface N. Now, an important property is
Allow it to cross itself the surface.
not by my conventions, by my conventions. So one of the first properties is avoidance, that the mean curvature flows will not bump into each other. Okay, so the assertion is this. So suppose you have two mean curvature flows. Say these are compact smooth surfaces, right? And let's say they're defined in the same time interval from T1 to T2. Okay, so the assertion is that if they're initially disjoint, then they remain disjoint. Okay, and the argument is simple. If that were false, well, if they're initially disjoint, there would be a first time when they touched, and then modulo translation and rotation, you can assume they touch at the origin with horizontal tangent plane, and locally, one of them would be the graph of a function. They're both graphs of functions where one function is bigger than or equal to the other, and that will tell you that the upper function would tend to have a greater tendency to move upward than the lower function, which means as you go forward in time, they separate, and backward in time, they would intersect, contradicting the first intersection time. Okay, so that's not quite rigorous, but basically the argument. So if you apply this, so if you take any mean curvature flow of compact surfaces, then that exists for only finite time, because you take your compact surface, you put it inside a large sphere, right? And that sphere will shrink down to a point. Since the guy inside has to avoid it, it has to blow up in finite time. And a variation on this avoidance is what you could call self-avoidance. Intuitively, if your surface is evolving, it can't bump into itself either, right? By essentially the same argument. So one way to formulate this would be the following, right? If you have a mean curvature flow, and the curvature remains bounded as you approach the right endpoint of this time interval, then, right, so that says the curvature is not going crazy, but you could imagine it could bump into itself. Well, this is asserting that doesn't happen. The curvature stays bounded. It will limit to an embedded surface, not something which is immersed. Okay. So now, if you have this initial surface M0 from this short time existence, you can, and uniqueness, you get an extension to a mean curvature flow, which is defined on some maximal time interval. Okay. 0t, and so as we saw, this maximal time is actually finite, right? This thing cannot be defined for all time, and so what happens as you approach that time, the curvature blows up. Okay, so this is called the blow-up time, and so now looking forward, what I plan to do is to look at some phenomenology. I want to look at some special cases or special classes of solutions, and we're going to be interested in what's happening at the blow-up time. Okay, so will be led to think about formation of singularities. So that will be the next phase of discussing what they actually look like or can look like, or what we know about that. And then after that, I want to discuss flow through singularities or beyond singularities. Okay. So just, I guess, I hope this is an unnecessary caveat, but let me put it in anyway. This is going to be, parts of the discussion are based on rather technical mathematics, and this is going to be just an informal presentation. Okay? Yeah.
I had a question from the last slide, but I think this slide is maybe indicating you're going to answer it on the next slide. I'm not sure. So you talked about the cylinder of the sphere. I'm just imagining if I had a torus, which is pretty thin, I sort of expect maybe the curvature would cause it to collapse to a circle, which is no longer a surface.
Right.
So how does that fit into this picture? Then the circle collapses, or you stop it then?
You would stop it then, but that is on one of the coming slides. So, other questions, comments? Okay. All right. So, but let's start with something simpler. And I've been talking about surfaces in R3. let's go down one dimension and think about curves evolving in the plane. So their mean curvature is just geodesic curvature, okay? And so the curve is moving with the velocity equal to its curvature, and that's usually called curvature flow, or curve shortening flow rather. And so, so the theorem is as follows. So suppose you have a curve shortening flow. So here, henceforth, this will denote the maximal time interval. So we have this curve shortening flow where the initial condition is just is connected, right? It's just a nice diffeomorphic to a circle. Well, then, as you approach this blow-up time, so from the previous slide, we know things blow up, right? But in fact, something very nice is happening. What's happening is that this guy, the diameter is going to 0, and it's approaching some point, and moreover, it becomes asymptotically round. Okay? So more precisely, modulo translation and dilation. Okay, so if you dilate it and dilate it and center it, it will this translated and rescaled guy will converge smoothly to a round circle. Okay.
The picture might be good, but you don't have to start with something convex here. You can take something that's very.
Yeah.
So those works for any curve.
And it makes it round nonetheless.
Yeah.
It becomes convex.
It always stays embedded. It's amazing.
I've given variants of this talk over the years. I tried to incorporate a video, and several times it just failed badly. So I just said, like, yeah, picture would be good. I do have some pictures later on. They're not even in black and white, so I've made progress. Right. So. Right. So now, what about dimension 3, surfaces in R3? Right. So Huysken proved that if you have a convex surface, so a compact convex surface in R3, then the same kind of behavior occurs. Okay. It shrinks down, and it shrinks down to a point, and modular rescaling, it's converging to a round sphere. Okay, as you approach the blow-up time. Now, then we come to the example Chris was talking about. So
it's named by Toby by any chance? It's not named by an English speaker, because any English speaker knows it's a wedding ring, not a marriage ring.
I think it was Tom Ilmanen. So
that's strange. He's a native speaker, but he lives in a German-speaking country.
But I'm not sure. Maybe I'm. So you take a small circle, and revolve it around the z-axis in R3, right? So that you want the diameter of the circle to be small compared to the distance to the axis, right? So then you revolve it around, you get this kind of thin torsive revolution, right? If it's really thin, if you look under high magnification, it will look almost like a round cylinder, okay? So just like the cylinder, it's going to want to shrink down. The symmetry will be preserved. And so when it shrinks down, it will actually collapse to a circle. All right. Now there are other types of singularities that can form, namely neck pinch singularities. So if you take a dumbbell-shaped surface, that will develop a neck pinch singularity. So now I'll use this animation, right? So you imagine you have these sort of two roughly spherical regions and this kind of roughly cylindrical region in the middle. And then, right as this shrinks, it sort of looks like a cylinder with smaller and smaller cross-sectional radius. And so it will shrink even faster, so you have an instability. And at blow up, you see something like this. Actually, there will be some place where things are going singular, but away from that, you actually have a smooth limit as t approaches the blow up time. Okay, so as soon as you have this example, then you want to try to understand better what's actually happening as that singularity forms. So here the standard approach is to try to zoom in or to blow up to get a better picture of what's going on at the singular time. So this brings us to parabolic rescaling. So this is a symmetry of the equation. So suppose you have a mean curvature flow, and you choose some scale factor r. Well, so then you can rescale that mean curvature flow. You scale spatially by r and time by r squared, and you get a new solution to mean curvature flow. So another way, which is often sort of more transparent is to think of this in terms of a space-time picture, right? So if we take...
Why is that the right rescaling? The heat flow is the other way around.
Well, time scales like, I'm scaling spatially by r. Maybe the space-time picture will make it clearer. Can I pause your question for 1 second? So think of taking this time-dependent surface and producing a space-time track in kind of the obvious way. You take the surface at time t and insert it at height t in space-time, so that sweeps out the space-time track. And then the assertion is for every r, if you take that space-time track and you apply this parabolic rescaling, right? You scale space by r and t by r squared, that image will also be the space-time track of a mean curvature flow. Yeah, so that's a parabolic invariance for the heat equation, right? And so that pushes you toward kind of parabolic geometry. Okay, so now you can apply this to the neck pinch, right? So let's think about that example from a minute ago. So let's say that you have a neck pinch occurring at the point x0, so that x0 would be where that neck was at time t0, okay? And let's perform this kind of rescaling, right? So let's first recenter things so x0 becomes the origin, the time t0 becomes the origin. So we do this spatial shift by subtracting x0 and then time shift by t0. And then we do the parabolic rescaling for various choices of this scale factor r. Okay, so this gives a family of rescalings. In fact, these mean curvature flows will converge to a shrinking round cylindrical flow. Okay, so where you have a round cylinder of radius square root of 2. So these kinds of singularities you can understand very explicitly using matched asymptotics. This was done a long time ago, but let me leave you with a picture. So this is the same neck pinch, but where you rescale in, okay? And then you freeze at time minus 1/2. That's supposed to be very convincing, right? So, okay. Right, so I mean the punchline is that from a distance you couldn't really tell what was happening, but in fact at small scales things are becoming almost nearly round cylinders. Okay, so then you can ask, well, what are other models or potential types of singularities? So you can look for, this leads you to the notion of a shrinking soliton. Okay, so a shrinking soliton will be just a mean curvature flow of this form. So for simplicity, you could take time to be defined to be negative. So this will become singular as time approaches 0 from below. And you just take some fixed surface n scaled by this factor, right? Remember, t is negative, okay? So this shrinking soliton is a mean curvature flow of this form, again, up to space-time translation, okay? So another way to say this is that if you look at this surface m-1, which is just n, that satisfies an elliptic PDE, which looks like this. The mean curvature flow, the mean curvature is the normal projection of basically the position vector over 2, or minus that, okay? So, but this is basically saying that you have a mean curvature flow, so it's evolving by mean curvature, but it remains unchanged up to scaling, okay? So it evolves, the mean curvature flow evolution is by rescaling. Okay, so that's what a shrinking soliton is. By definition, well, we already have seen examples of this, so the shrinking round sphere or shrinking round cylinder, but there are many other examples. So one of the first interesting examples was constructed by Angenent, right? So if you think about this marriage ring, it's a thin torus, right? That kind of pinches in one direction. Now imagine revolving a circle and around the z-axis, but letting that circle approach without touching the z-axis, right? When it gets really close and you zoom in, what you'll see is you'll see almost a straight line, right? Where that circle is approaching the z-axis. If it gets really close and you revolve that around the z-axis, what you'll see is something that looks very much like a cylinder, okay? But around the z-axis, that will have a tendency to pinch. Around the z-axis, you'll see a neck pinch, okay? So why am I mentioning that? So somewhere in between this thin torus and this kind of fat torus, there's a torus where these two tendencies are exactly balanced, okay? And that's the Angenent torus, which will just shrink itself similarly. Neither tendency will get ahead of the other, okay? And then much later, other examples of shrinking solitons were found. So in particular, there were some examples found by Kaplan, Muller, and Nguyen. So let me just show you the picture. So their example looks like this. So you should think of, the plane and a sphere centered at the origin. So those two guys will intersect along a circle, right? Along the intersection locus, you see, right, two surfaces intersecting orthogonally. And the idea is for large genus, you desingularize that intersection with a second Church surface, okay? And so they show that for large genus, if you do it at a small enough scale, you can actually get a solution to this Schrinker equation. So near infinity, when the genus is large, near infinity, it will look conical where it's a cone over a very small perturbation of the equator, okay? It's not asymptotic to a plane, it's asymptotic to something which is very close to the great circle, okay? But anyway, these things exist, and they're models, potential models for the formation of singularities, okay? And so from a philosophical point of view, it seems hopeless to try to classify all of these shrinkers. There's probably no more hope of classifying them than there is classifying minimal surfaces in R3, okay? Yes, well, we'll get to that, the very initial question. Okay, so now I want to, so thus far I've discussed candidates for what things might look like at a point of blow-up. Now you can ask what happens in general at blow-up. What can you say in general about what singularities look like?
Just one other comment. So these shrinkers are kind of invariant under the mean curvature flow, so are they kind of minimal surfaces in some sense?
They are. They're minimal for some conformal metric. Yeah. Okay, so this leads you to what people call singularity analysis. Okay, so if you're familiar with the theory of stationary or minimizing integral currents and the theory of monotonicity and tangent cones, this is a variant on that. If you're not familiar with it, just ignore everything I just said. Okay. Okay. So here's the setup. So let's give ourselves some point x0, t0, base point in space-time. Okay. And then we'll look at a backward heat kernel centered at that point in space-time. Okay. So with the caveat that this is not quite the backward heat kernel in R3. This formally, it looks like the backward heat kernel in the plane. Okay? And the reason is we're going to be integrating it not over a region in space, we're going to be integrating over a surface. Okay? So you want the two-dimensional heat kernel for that reason. So now suppose you have a mean curvature flow. So he's going to define the Gaussian area. So for any time prior to this T0 where this backward Gaussian is defined, you just take the integral of that kernel over your surface at that time. Okay? So we look at this Gaussian area based at x0, t0 for the mean curvature flow at time t, right? What do? You take this heat kernel at time t, and you integrate that over the surface at time t, okay? With respect to area. Now, so Hiskin showed that this is actually monotonic, okay? So if you take time t1 less than t2, okay, then this area at the later time is less than or equal to the area at the earlier time. And equality holds only if you're actually on a shrinking soliton in this time interval, okay? So between T1 and T2, you see a shrinking soliton. And this follows just from a computation. The computation is that the time derivative of this Gaussian area is minus this integrand here, and the integral of this thing here, and that vanishes if and only if you're on a soliton, okay? So one of the this is very useful, just like the monotonicity formula for stationary currents or minimal surfaces is useful. But one of the first consequences is that this quantity, the Gaussian area, has a limit as you approach the base time t0. Okay, because this Gaussian area is not increasing and it's bigger than or equal to 0, right? So it has a limit, and that's the Gaussian density at x0, t0.
So what is the geometric picture of that integrand to 0?
Well, take the case where x0 and t0, x0 is the origin, t0 is 0. And then it's basically just the equation I had before.
Yeah, but I didn't understand it.
It's saying that, so you're at the origin, you take the, here's the origin, here's the surface, here's the point x, so you think of that position vector, and you take you project it onto the normal direction. Okay, you take the orthogonal projection of the position vector onto the normal space at this point, right? And that should be the mean curvature vector up to a factor of 2. Okay, it's an elliptic equation. Okay, so we have this Gaussian density. Okay, so now this leads to tangent flows or blowups. Okay, so let's say we have a smooth mean curvature flow, right, which then blows up at some time capital T. All right. So first, let's take some time t0, which is before things blow up. Okay, so at that time you still have a nice smooth surface. Okay, and then let's use the spatial base point to lie on the surface at that time. Okay, right. So then this Gaussian will concentrate as you approach t0 from below. It's going to concentrate at the point x0. Okay. And if you kind of zoom in, of course, you have a smooth surface. So under zooming in, it will look more and more like a plane. And you're integrating the Gaussian over that. It's not hard to see that's going to converge. That's the limit is going to be 1. Okay. So at the smooth point, the density will be 1. On the other hand, now if you take t0 to be the blow-up time, and okay, and you have a singularity forming near there, the density could be larger than 1. Okay. Okay, so another feature here is that the Gaussian area is scale invariant. So that means if you take a mean curvature flow in a point in space-time, now scale everything by some factor r, or translate whatever, and look at the corresponding times, the Gaussian area will be the same. Okay? So now, right, so let's think about what happens when we do what we did several slides ago. You have this point in space-time, you take a sequence of scale factors going to 0, and you look at the corresponding rescalings of these, translated guys, right? The Gaussian area of these rescaled guys corresponds to the Gaussian area of the original flow near that point in space-time. Okay? And so therefore, these guys will have asymptotically constant Gaussian area as r goes to 0. Okay? So again, if you're familiar with minimal surfaces, it's like the fact that the rescaled minimal surfaces that will have a sequence, asymptotically, their area ratios will converge to the density at that point. Yeah. There's a question back there?
Can you explain why it's like a density? Because usually when we talk about density, we normalize it by something like comparing with the area of like a disk.
It's basically an etymological question. I mean, you have it's scale invariant. I mean, maybe that's one rationale for the choice of wording, but okay. Other question? Yeah. Okay, so
it's a probability measure.
Yeah.
Oh, okay.
But then you're taking the limit. I mean, yeah. Okay, so the upshot here, right? So I'm saying that this is scale. These guys, these family of rescalings will have asymptotically constant Gaussian area, right? So as a following consequence, right? If you have a subsequential limit of this family, right, it will be a limit of guys with asymptotically constant area. So the limit will have constant Gaussian area. Okay. So we're kind of rescaling. If you can pass to a limit, it will have constant Gaussian area, and therefore by Huysken's theorem, it will be a shrinking soliton. Okay? So, and that's called a tangent flow. Okay? But with a key caveat, like nobody said that you can extract a limit. All right? But there's an important result of Illman. In 95, he showed that this rescaled family will actually converge subsequently to some smooth shrinking soliton. Okay? But with a caveat, he didn't show that you had smooth convergence. He showed that you have convergence of measures. Okay, so you think if you have a surface that has a surface area measure, right? If you have an evolving surface, you get an evolving family of measures, okay? And so if you have a sequence of evolving surface measures, you can talk about weak limits, okay? And that's what he did. So he showed that the associated evolving surface area measures converge weakly to the evolving measure of the shrinking soliton, but maybe not the area measure itself, but possibly some integer multiple of it, okay? So, and he said, he made this caveat, right? The reader should be aware that the convergence to blow up might not be smooth, okay? There might, in principle, be small necks and other topological kinks that pinch off and disappear in the limit, okay? So that's a statement about what he proved. But he also conjectured that, in fact, the multiplicity of this limit is 1. It's not 2 or anything higher, but it's 1. And it was known at that time that if this conjecture is true, if the limit has multiplicity 1, then in fact the convergence is smooth, after all. Okay? But anyway, so this is the multiplicity 1 conjecture.
What's that about being smooth? It's what?
That if you happen to know the multiplicity of the limit is 1, then basically by Brocchi regularity, that implies that the convergence is smooth. Okay? Okay, so now I want to shift gears and talk about flow through singularities. Okay, so let's start with the cartoon, right? So let's look at the picture we had before. So you have the neck pinch singularity, right? So we have some surface left. As I said, there's smooth limits, so maybe you want to continue the flow. Okay? So this is the idea of...
That's not what happens, is it?
That's what you'd like to happen.
Oh.
Okay, so...
The curvature was near that point, was pushing you the other way.
Well, I mean...
That makes it smooth out.
Yeah, exactly.
It's like pulling out
Yeah.
a wrinkle.
Right.
Okay.
Right. It's like these little fingertips will retreat.
Okay.
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 Okay, so, right, so that's a picture, but so what's the motivation for this? So, right, from a PDE viewpoint, right, so far we've been talking about classical solutions to some geometric PDE, geometric PDE, but singularities have arisen naturally, so then you want to have a theory that allows for singular solutions, right? So you want to talk about weak or generalized solutions to mean curvature flow. This is a project which has been going on for many decades with other equations, with minimal surface equation, harmonic maps, harmonic map heat flow, Navier-Stokes, and so on, right? It's a standard project in PDE. Now, from a physical point of view, if you're thinking of these as mathematical models, right, then the first example you think of with the soap film pinching off the singularity forms, you have a neck pinch, but then it continues evolving. And so if you're trying to model that mathematically, you'd like to have a discussion which covers that. And then also, essentially, any mathematical application requires a theory that goes beyond the blow-up, right? If your theory just stops at blow-up, you can't really use it for much of anything unless you set things up so that that things are very special and singularities are very highly restricted, okay? So that's the motivation. And so this is a project that's been underway for basically since Brocchi's work. People have been working toward trying to make sense of flow through singularities. And so over time, there's some conjectures that emerge. Some of these appear in print in different forms. Some of them were basically were folklore. But right. So the first one would be, I'll call existence in regularity, which would say, well, there's a flow that isn't too horrible. Okay, a flow that looks kind of reasonable. So here reasonable means if you look at the space-time singular set, it shouldn't be too big. It should be contained in a finite set of curves. Okay, and the motivation for this, well, we already saw the example of the thin torus, right, which collapses down to a circle, which has dimension 1. And no one has ever been able to come up with a plausible scenario which looks much worse than that. So I think for a long time that was really the motivation for this form of the conjecture. I mean, there was much better evidence later, but anyway. So then the Multiplicity One Conjecture is an extension of the one that we already saw. So this should say, tangent flows have multiplicity 1 even after the formation of singularities. Then the generic singularities conjecture comes back to, the earlier question, right? So here, so we saw these complicated looking, shrinking solitons, which could model singularities. They could actually arise, right? But you could naturally ask, if you give yourself the latitude to take an initial condition and perturb it a little bit, is it possible that then, okay, singularities may still form, but they'll be a lot simpler, okay? So that's the motivation. So this version of the conjecture is attributed to Huysken. So if you take a generic initial condition that singularities should be simple, they should be modeled on shrinking round spheres and cylinders, okay? And then another conjecture is about two spheres. So if the initial condition is topologically simple, if it's diffeomorphic two sphere, then in fact the flow shouldn't just exist, it should be unique and should have these simple singularities, okay? So if you have flows with complicated singularities, that requires complicated topology to begin with, right? So I just want to point out these are not really mathematical conjectures in any conventional sense, and the reason is they're incoherent, right? Because they're referring to a flow which has not yet been defined, okay? So it's maybe you can think of this as kind of a mathematical physics project where you're trying to construct something which will meet some list of specifications, right? So these aren't conventional conjectures. That doesn't make them less interesting, but
Then a mathematical question. Find the right definitions so that something is
right. So now I want to talk about the progress on this. First of all, if you want to talk about flow through singularities and discuss it, you first need to settle on a definition. Yeah, question?
I just had a question about the generic. So that A being a conjecture entails that these other shrinking solitons are not expected to be stable.
Right.
Okay.
Right. Okay, so there are three approaches I want to mention are Brocchi flows, level set flow, and flow with surgery. So Brocchi flows came first historically, but let me start with level set flow since it's easier to get a handle on. So this came around 1990, and it was further developed by Ullman and White. So first, a weak set flow. So the things that are evolving here, I mean, if you're going to develop a theory, you have to decide what's evolving. What's evolving here will be a closed set. Okay, so weak set flow is just some evolving family of closed sets. Okay, so you have k sub t in some time interval, such that the first requirement is the space-time tract should be a closed subset of space-time. Okay, and the second condition is that it should avoid smooth flows. Okay, in the same sense that we had before. So if you have a smooth flow defined in a time interval t1, t2, which is a subinterval of the time interval I in which your evolution occurs, and if these two guys are initially disjoint, they should remain disjoint. Okay, so now we're positing this avoidance property, which held before in the smooth case. Okay, and so now the level set flow with some given initial condition C is just the maximal weak set flow starting from C. Okay, so you take C, let's say a compact set. It's not hard to show that there's a maximal weak set flow. You take all of them, you take union, and then take closure, and that's still a weak set flow. Okay, so that's basically a canonical object. So okay, so some properties. So first of all, just from the definition, you have existence and uniqueness of solutions. Okay, so if you're a PDE person, this sounds very nice, right? Often you have to fight quite hard to get this. So the second thing is like a reality check. If you take the level set flow starting from a compact smooth surface, well then this level set flow will agree with the smooth mean curvature flow until blow up. Okay, so this is a reality check that you're consistent with the smooth theory as long as it's.
How do you prove that?
I mean there are a number of. I mean it's basically using the perturbations of this guy as barriers. That's the rough idea. So also level set flows will avoid each other, so that's good. So that we know that level set flows will avoid smooth flows by assumption, but they will avoid each other, in fact. But that's all. So far, it's all good news. The bad news is that level set flows can fatten. Okay, so what that means is you could start with, say, a nice smooth surface. The level set flow is nice and smooth. The singularity forms, and then after that, you see something which has non-empty interior. Okay, so if something has non-empty interior, it doesn't look much like a surface, right? And it's not, right? So that's a big problem. And to get a rough idea just of how this works, so you can think, dropping down from R3 to R2, think about the union of the two coordinate axes, right? If you want to run the level set flow for that, so, well, first notice you could imagine evolving this as follows. You kind of break these two things apart into these two guys. Union the positive x, the positive y, and positive x. Under curve shortening flow, that's going to round off like this. Okay? And similarly for the other quadrants, these smooth mean curvature, these smooth curve shortening flows can be used to push any other curve shortening flow away from the vertex. Okay? And if you use this fact, what you realize is that the level set flow will actually be the region which lies between these four curve shortening flows. So the union of the two coordinate axes will fatten instantly. Okay? So that's not very convincing because the initial condition was already singular and was kind of dubious. But in fact, this same thing can happen for a compact smooth surface in R3. Okay, this was discovered shown by Ullman and White. So, but you need a surface of high genus, and then this phenomenon can occur. Okay. So I want to mention that. So there was an idea going back to Ullman, which is a variation on this, which at least does not have non-empty interior, and that's the notion of an outermost or innermost flow. So here, the idea is you take your compact smooth surface M0, and now, right, so you look by Jordan separation, it's going to bound some compact domain, right? And then you flow that domain, okay? So you look at the level set flow of that domain, and you take the space-time boundary of that, and that's another candidate for reasonable sounding flow. At least it doesn't have non-empty interior, okay? So that leads to the notion of an outermost flow, and you can do the innermost flow similarly by looking at the non-compact domain bounded by this guy. All right, so now, all right, I'm going to have to speed up a little. So another approach is Brocchi flows. This is from Brocchi's 1978 book. So here instead of evolving a surface or a closed set, we're evolving a radon measure, but subject to some conditions. So first of all, at each time this radon measure should be an integral varifold. Okay, an example would just be the area measure of a smooth surface. Okay, but more generally, so an integral varifold is just a measure which is the sum of nu i's, where nu I is a surface measure of a C1 surface restricted to some compact subset. Okay, so basically, an integral varifold is, I mean, you can think of those as like surface fragments. So the integral varifold is like a superposition of surface fragments. And so the second condition is that the distributional mean curvature of this measure mu t should be absolutely continuous with respect to mu t itself at almost every time. Okay, so the point is these are not arbitrary radon measures, but they're radon measures which have some distributional version of mean curvature. Okay. So that's, and then then you have this requirement. So it's instead of being just an arbitrary vector value distribution, it should be vector value distribution, absolutely continuous with respect to mu t itself. So I mean, I was going through this at kind of high speed. The idea is, if you have an integral varifold and you give yourself some compactly supported vector field, then you can flow this varifold in that vector field, and you can. There's a first variation formula. Okay, it makes sense. And so therefore you get some linear functional on these compactly supported vector fields, and that gives you a vector value distribution. Anyway, maybe I'll skip over this. And then you get sort of a weak version of the mean curvature flow equation, where you take some test function, and in the case you have a smooth mean curvature flow, you check that this equation holds here, and Brocchi basically takes that same equation and applies it in integral form. Okay, so the properties. So you have existence of Brocchi flows for any smooth surface. You have a Brocchi flow with that as initial condition. The monotonicity formula actually applies, which is an advantage of this approach. over the level set flow. There's an epsilon regularity result that holds for people who are familiar with this, the geometric measure theory or PDE. You have good compactness. But the bad news is that these Brocchi flows can be very badly behaved. You can take, say, a shrinking round sphere and then at some moment just throw it away. And that's a perfectly legitimate Brocchi flow. Okay? So the condition is really kind of under determined. I mean, the Brocchi flow condition is really inadequate. But there's a even more serious problem, which is that the flows, it's not clear. You can construct these Brocchi flows, but it's not clear how to construct them in such a way that the regularity theory will apply in most places. Okay, so that this issue of multiplicity actually goes back to Brocchi's original work. Okay, all right. So let me just skip that. So there was now I want to talk about mean convex flow. So this is, so if you have a domain with smooth boundary, it's mean convex if the mean curvature vector field points inward everywhere. Okay, which means that under mean curvature flow, the surface will start to move inward, or the domain would start to shrink. Okay, so the surface is mean convex if it's the boundary of a mean convex domain, and so the obvious example of something that's mean convex is just something that's convex. But the condition is actually significantly weaker. You can construct some dumbbell type surfaces that we saw earlier in that animation, which are actually mean convex. Okay, so this condition is weak, sufficiently weaker than being convex to allow those.
Near the end of the dumbbell that they're pointing out.
If you do it carefully, it will be. You can make it mean convex. So, yeah. So in kind of about 25 years ago, White made a major breakthrough. So he showed that in this case, essentially all the conjectures that I had up there before hold. Okay, so if you look at the level set flow starting from a smooth mean convex surface, then the level set flow doesn't fatten, so this pathology does not occur. Okay, you have a canonical associated Brocchi flow. The Huysken's singularity statement about all tangent flows being spheres and cylinders is true, and the space-time singular set is what you'd like, right? As Hausdorff dimension less than or equal to 1. Okay, so now I want to talk about the new results. So the first is kind of a new. The first ingredient is really a new approach to flow through singularities. So we have a new kind of object here, which we call almost regular mean curvature flow. So this is going to be a weak set flow. So we have a subset of space-time here, okay? And it satisfies two conditions. The first one is pretty easy. It just says that for almost every time, the time t slice is a compact smooth surface, okay? And so the second condition involves some kind of regularity scale. So I need to introduce some definition. So the parabolic R-ball centered at some point x0 t0. So this is going to be, so p of x0 t0 r. This is going to be the usual R-ball centered at x0 crossed a two-sided time interval, right? So it's forward and backward in time duration of r squared. Okay, so you think in the picture space-time, it's like a cylinder in space-time. And okay, so the parabolic regularity scale R log at this base point is as follows. So it's the supremum of all radii such that when you look at this parabolic region, so this cylindrical region in space-time, you intersect it with any time slice of your weak set flow. What you see should be regular, should be a smooth surface, okay? And second, the normal injectivity radius should be comparable, at least comparable to R. Okay, so normal injectivity radius of a piece of smooth surface is just you've pushed the surface in the direction of the normal vector in both directions, and you see how fat you can get before it starts to run into itself, right? So normal injectivity radius, okay? So from this definition, you see that if your point is a singular point, okay, then this radius is just 0, okay? And also, if you look, so A here is the second fundamental form. The second fundamental form is bounded above, say, to within a constant, by 1 over this regularity scale, okay? So you can think of 1 over this regularity scale as being some kind of enhanced version of the norm of the second fundamental form. Okay? So the second condition is that that quantity, this kind of pseudo curvature, pseudo second fundamental form, is in spacetime L2. Okay? So you take this R log to the -2, you integrate that over the surface at time t with respect to Hausdorff measure, and then integrate over time. That should be finite. Okay? So that's the second condition. And okay, so you get, it's easy to see, you get some associated Brocchi flow. And so we have, for these guys, we have a compactness theorem. So if you have a sequence of these flows where the initial conditions converge smoothly, then they will converge subsequently to another such flow. Okay? And we prove the multiplicity one conjecture for these objects. If you have an almost regular mean curvature flow, then tangent flows are multiplicity one shrinking solitons, right? So we get the multiplicity one conjecture. Okay, let me skip these other statements. And now we combine this with a number of earlier results. So there's been kind of a remarkable development over the last 10 or so years, right? I mean, I'm just mentioning only some of them. This is fundamental work of a bunch of people, Kolding, Minikazzi about regularity, Brendel about multiple contributions. And then kind of in the last few years, there were a series of results. In any case, we combine our work with this previous work, and then we can answer all of settle all the conjectures in that earlier slide. So starting with, so if you have an outermost or innermost flow, okay, then that is an almost regular flow, and we have the regularity statement. So this almost regular flow will have the same kind of regularity as the mean convex flows that I referred to in the earlier slide with White's work. And so for general initial conditions, it's not true that the tangent flows are shrinking around cylinders shrinking around spheres, right? Because we have these examples, but there are most finitely many exceptions. Okay. And
that's bad news or good news?
it's a fact of life. It's a fact of life. So I mean, there are examples. Yeah. So then generic regularity, right? So if you have a compact smooth surface, okay, then you can approximate that by in C infinity by a sequence of smooth surfaces, right? Such that if you look at the level set flow, Kj starting from Mj, then first of all, that's non-fattening, right? So therefore it's an almost regular flow, okay? And so it has the regularity that was on the previous slide. But moreover, now all tangent flows are round spheres and cylinders, okay? So that's Huysken's conjecture. And then in the two-sphere case, if you have a level set flow, right, where the initial condition is diffeomorphic two-sphere, then the level set flow is non-fattening. So again, the same assertions hold before. And then all tangent flows are spheres or cylinders, okay? So I think I'll stop there.
Any questions for Bruce?
Are there any problems left?
Well, there are lots of interesting things to look at. So, I mean, one of them is, so in this theorem here, right? So Huysken's conjecture was that the tangent flows look standard, right? So you see either shrinking round spheres, or you see. So that says if you take a singular point, right, and you do the zooming in process, and take a subsequential limit, what you see is either shrinking round sphere or a shrinking round cylinder. Right. And actually, they have multiplicity one, so actually the convergence is smooth, and you can say significantly more than that. Okay, but an enhanced version of this would say that if you take a smooth surface, make a small perturbation, then there are actually only finitely many points in space-time which are singular. Okay, it's a bit like a Morse function. Okay, and so the points are either
For the minimal.
for generic mean curvature flow. Yeah. Okay, and this is what's here is it's quite far from that. So that's one example of a question. Another would be trying to understand. So I mentioned this fattening can occur. It's a fact. That's also a fact of life. But one would like to understand the origin of the non-uniqueness and
Generically, there are only finite points that are these pinch points where the spheres collapse.
right. So that's a generic behavior, but you can still ask about the general behavior. And so even in the mean convex case, there are questions about that which are very natural.
So in this generic initial data case, can you actually then define a flow through singularities at these finite collection of points?
No, I mean it's already defined. It's already defined. In fact, in this flow, okay, so the fact that it's non-fattening actually implies that there's a unique, almost regular flow with that initial data. So I didn't really emphasize this, but not only do you have the statement about the tangent flows, but actually you have uniqueness. Whereas in general, you have non-uniqueness.
With fattening.
Yeah, I mean, it's a bit complicated, but roughly speaking, fattening is the result of non-uniqueness of Brocchi flows.
Go through the singularity generically.
Generically, that won't occur.
So if you look at the wedding generic case, is there a notion of flowing through that singularity, or does it just end when you get to the circle?
Yeah, I mean, one of the basic things about mean curvature flows is a gradient flow. Area does go down, so it's going to zero. So any continuation should have zero area. So
the tangent flow in that case just prolongs, makes death look like it's forever away.
No, the tangent flow, when you zoom in, like you shift to 0, 0, that the tangent flow will be a cylinder which disappears at time 0. Yeah.
That circle can be shrunk, but that's like a completely separate problem. You're not generically going to get something.
Right.
You don't switch to geodesic.
Yeah, I mean, you could try to introduce something like that if you wanted. Yeah.
So I'm assuming the numbers 3 and 3 minus 1 are really important in all these theorems, as opposed to K and L or something?
3 minus.
Surfaces in 3 space.
Yeah.
As opposed to anything other combination.
Well, I mean, one could hope to. I mean, it's very natural to try to do this in Rn, particularly in R4. But there are a couple. I mean, there were some ideas about how to do that, but there's a piece of this which seems to use the fact that you're on a surface. Surfaces have genus, right? And that.
But also, if you up the codimension, it's presumably a different problem.
Yeah, that's a. I mean,
it's hypersurfaces in Rn.
Yeah. I mean, the higher codimension looks much worse.
Codimension 1 is.
Were there any known examples in higher dimensions which throw a monkey wrench into it automatically, or say that are dangerous?
Well, I mean, you can just have simple things. I mean, regarding multiplicity, I mean, if you have a curve, even in R3, there's no reason why it can't start out embedded and then you see at a moment.
Like an n-1 surface in n space.
Oh, yeah, no. Yeah, codimension 1. No. Yeah, codimension 1. No, it's wide open. Yeah, I don't. Great.
So it's sort of related to the fact that even for minimal submanifold, codimension 1 is much easier to handle than higher codimension. So actually, since this so-called marriage ring example came up again, so if you take a small perturbation of that, though, does one know actually what happens? Does it break apart into?
So yeah, I mean that's a mean convex case. So there, the tangent flows are going to be spheres and cylinders. You can go quite a bit further than that, but as far as we know. Right, so I believe this is correct that right now there could be uncountably many singular times as far as we know, but the singular times have a Hausdorff dimension of most 1/2. But so another conjecture is that in general there will be only finitely many singular times, and at each of them you see this something like either a component shrinks down to a point in a round way, or you could have finitely many such, or you could have finitely many kinds of neck pinches occurring, or you could have, the surface, could collapse down to a curve. There's a fun question, so we have these examples of toroid revolution, which collapse to circles. It's unknown if there's any other curve in space than a circle, which can arise as a limit of a collapsing surface like that. That's also an open question.
So if you take like a knot and like thicken it, that will collapse to a knot or something?
No, generically no, but it's unknown if there is any curve other than a round circle, which could arise as a limit. Yeah, sorry.
So I have a question about flow through the level sets for the dumbbell example.
Yep.
Because it seems like it breaks apart into things that are, balls. But then if you put a bigger sphere around that, how does the non-avoidance work? It seems like these two balls should somehow come together, but how would they?
Well, they would, this larger thing, to engulf it would have to have smaller curvature. Larger radius, smaller curvature, it's moving more slowly. So by the time it arrives, they'll have already disappeared.
Oh, I see.
And what's the status of this conjecture of White's, that if you start with some initial data that's a topological S2, that there's better behavior?
Yeah, no, that was the two-sphere result.
I see.
So that you can think of it different ways. There's a unique, if you take something that's diffeomorphic to two-sphere, it doesn't fatten, but there's a canonical, almost regular flow. So that the non-fattening is sort of hiding the uniqueness, non-uniqueness narrative, which was a major complicating factor in this whole discussion.
One more basic question. So if we have some convex initial data, someone compute to which point the shrinking occurs?
All right, I can say this. You could ask the same question at R2,
Yeah.
right? So it's sort of an emphatic negative answer to that. There's actually a paper by Griffiths and I want to say McClelland as co-author. So he showed that there is no formula. Yes, it shrinks down to a point, but there's no formula for that's an integral formula involving finitely many derivatives of the initial data. So if you look up Griffiths, it's around 1990. So.
Other questions? All right, if there are no other questions.